where n is the dimension of the matrix. So, in a 4 by 4 matrix, which is perfectly consistent, the maximum eigenvalue would be 4. It can be proved. We don't prove this, because this is some basic matrix theory. And don't worry why this is obtained, how it is obtained, but let's just note that if the matrix is perfectly consistent, this is what we find. On the contrary, if the matrix is not consistent, then lambda max, which is the maximum eigenvalue, is greater than n. The more the matrix is inconsistent, the more lambda max is greater than n, which means that lambda max minus n becomes greater than 0. Now, you can compute a consistency index, which is simply lambda max minus n divided by n minus 1. This consistency index would be 0 if the matrix is perfectly consistent, would be higher than 0 if the matrix is not. Okay, now this consistency index is compared, you see the equation number 3 behind me, let me put it higher in the screen, is compared with at the denominator the quantity Rin. What is Rin? It is the consistency of a matrix that is randomly generated under the only condition that it is antisymmetric. Meaning that if you don't care at all about consistency and you just shot the numbers by just taking care that the matrix is antisymmetric, of course you obtain an evaluation which is random. Doesn't care by consistency. This is a baseline. And this consistency index of a completely random matrix, the value is given in this table here, depending on n. So this table gives to you the reference value. So, what you see is that if the matrix, let's look at the equation number 3, and this left-hand side, CR, depending on A, is our consistency index that we want to compute. So this is the result that we have to find. And if you look at the relationship, you understand that if the matrix is perfectly consistent, then you get 0 for CR, because it will be 0 CI. Look at the definition of CI, lambda max minus n. So lambda max is equal to n if the matrix is perfectly consistent, so CI is 0 and therefore CR is 0. On the other hand, if you have a matrix that is really inconsistent, then Ci tends to Ri, which is the consistency of a matrix that is randomly generated. And therefore you have an upper value for CR, which is 1. If you get to the value of 1, it means that your matrix is inconsistent, because it is consistent like a matrix that was randomly generated. And therefore you have to be close to 0 with this CR. Of course, and the indication is if CR is lower than 0.1, that's fine. Otherwise, if you compute your consistency index for the matrix, and tomorrow, parentheses, bring your PC tomorrow, we will make some experiment, because it's very easy to compute in Excel or R eigenvalues and eigenvectors. So we can make an experiment. Even if we don't remember what they really mean, eigenvalue and eigenvectors, we can make an experiment. So tomorrow we will make an experiment. So basically, if you see that your consistency index is greater than 0.1, then it's better if you go back to your evaluation and try to make it more consistent. So this is the moral of the story. And let me go back to this paper in Italian that I presented to you. This is an example of application of pairwise comparison and with a prior determination of utility functions. And the determination of the utility function was done in a different way, by several interviews to the people, and not through pairwise comparison. The pairwise comparison was used just to determine the weights. And in fact, you see in this paper several criteria, and you see the criteria for the hydropower plant, including preservation of the environment, including economical benefit, including the noise, including the duration of the construction works, which cause, of course, if they last for a long time, they cause some problems to the people, etc. And here you see the utility function for each indicator. So for each one of the considered indicators, you see the utilities, and then there is, finally, and these functions, again, were determined with interviews, and then at the end you have the determination, you see definizione dei pesi, which means weight identification. And here there is explained how it was done, this determination, through the pairwise comparison. And you see here the weights, etc. And then the optimal design solution. And this was for me an interesting experience, because this was a paper that was written with a professional engineer that contacted me just on this purpose. He wanted to seek assistance from the university because he wanted to write a paper on this experience that he made. He wanted to write a scientific paper on this experience that he made of using the pairwise comparison for designing a small hydropower plant. And therefore I learned about pairwise comparison, and I was motivated to study more, and then I decided to teach also the student this opportunity, because I found that it's really interesting and in fact is increasingly used. Okay, this is what concerns pairwise comparison. Let me check if, because I forgot yeah, it's still recording. I forgot the SD card, but the camera can work on internal memory, so for a limited time. Now, so tomorrow I will introduce an exercise. It will be the last one, because next week we will have just lectures, and also on the last day I want to provide a summary of the course and some discussion. And therefore, what we did with these last two lectures is, I want just to summarize, is to introduce a possibility for solving multi-criteria decision problems. I said that this is not the only way, this is not the only possible solution, and in particular, I just want to stress that there are other solutions which are based on keeping the criteria separated. In this case, we wanted to join the criteria in only one objective function, which is the sum of the utilities, but it's also possible to keep the criteria separated and to apply methods that allows you to find the best compromise in terms of analyzing the connection among criteria and feedbacks, but without joining the criteria. I'm not I'm not dealing with these methods this year because we dedicated some room to groundwater, which usually was not considering, and therefore I decided just to stick for this part on this type of optimization based on merging the different objectives. But now there is another issue that I want to introduce, which is dealt with by a PowerPoint file that is already available in my website, was already available at the beginning. And this is related to decision under uncertainty. Because so far we didn't consider uncertainty in our treatment. Basically, we considered the case in which we have one criteria or multiple criteria for taking a decision. But you know, we also have the problem that the information that is required to compute the numerical value of this criteria is uncertain. And let me give to you a very easy example. We are used to deal with an objective function, with an objective function, which in our first example was an economical benefit. And I gave to you some analytical expressions for computing the economical benefit. And you may remember that we introduced an analytical function for the benefit, which I introduced because it was easy to treat analytically. But this function contained a couple of parameters, A and B. So the net benefit was depending on two parameters, A and B. And we didn't consider the case in which A and B could be uncertain. Meaning, instead of having a fixed and certain value, they may be uncertain. So this is always the case in hydrology. Because hydrology is an uncertain science, I mentioned to you this problem, and therefore every data with which we work with is basically uncertain. So a relevant issue is how to take a decision under uncertainty. Of course, it's different. The story is different with respect to the situation in which you have just fixed values for your information, in the situation in which you don't have your information is certain. So, apart from this introduction, which I think we can skip because, of course, there is written here why our information is uncertain. We know that. So basically, let's look at the second slide, which represents the possible solutions, and just as an introduction. First of all, we should reduce uncertainty as much as possible, of course. But let me say that eliminating uncertainty is not possible. I can say this for sure. And I would say that it's not possible to eliminate uncertainty, first of all, from a practical point of view, because it's impossible when you measure rainfall, river flow, when you take any information related to the catchment, it's impossible to eliminate the measurement error. It can be reduced, and in fact you see that here the aim is to reduce, but it cannot be eliminated. And also there is another thing that I would like to introduce and to mention, just as a philosophical consideration, which is not really useful from a design point of view, but I think it is useful to get a better perception of the complexity of hydrology, the complexity of the systems we are working with. And the consideration that I would like to make is that I am convinced, but this is a debate, an open debate in the scientific community, so this is, let's say that this is just my opinion. I am convinced that even if we were able to take measurements which are error-free, in any case, hydrology would be uncertain because it's uncertain in the water cycle. So there are some processes in the water cycle that, in my opinion, are random, like the movement of the clouds or rainfall, to me, is random, or even, for instance, the flow path that the water follow for going downstream, either over the surface and under the surface of the ground, I think there is some randomness in the choice of the different paths, because, you know, sometimes it may suffice just some wind or some change in the behaviors of the soil, and then the flow path is different. And therefore it's, or if you think to a drop that is falling over the divide between two watersheds, sometimes to decide whether to go downstream on the left rather than on the right is just a matter of casuality. So I think there is indeed a lot of randomness in hydrology. There are other people who say that this is not true because it's a physical process, and then people say, you know, it's regulated by physical law, and physical law are not uncertain. But this is not really true, because there are some physical laws which are uncertain. And if you think to hydraulics, hydrology is based on hydraulics, the Navier-Stokes equations are not perfect, are not exact. So basically I think there is uncertainty cannot be eliminated. So let's forget about eliminating it. And then what are the possible solutions from our technical point of view of engineers? So the first solution is the solution that implicitly we adopted so far. Use expected values of the uncertain variables. Like, I estimate the parameter A, there is some uncertainty, I use the expected value, which is average, basically. And then I assume that this expected value is a certain value for the variable, is a certain value for A, for the parameter A. And of course, if you do that, your decision would produce the expected effects on average only. So basically, your decision will be right on average, and then in the remaining cases it will be wrong. This is an extreme point of view. If you just take averages, it means that you are right on average. But you know, to be right on average is not a comfortable situation, especially if you have to pay for your mistakes. You don't want to be right on average. You want to be right in the vast majority of the cases. And the vast majority is much different from average. Therefore, another approach is to use the most precautionary values. Like we say in Italian, approccio a favore di sicurezza. Means that you use an approach that maximizes your safety. Your, let's say, safety. Let's drop your, let's say, safety. Be careful, this type of decision may induce a significant loss of benefit. Of course, like driving a car. If you want to minimize the risk, then you have to drive very slowly. And therefore you don't get to the target on time. So you get less benefit. And the same for water withdrawal. If you want to minimize the risk, you wouldn't take any water from the river. Because, of course. And therefore you need to seek the help of quantitative methods to take the best decision. Probably you can't take just the average, but at the same time you can't just take the most precautionary value, because in many instances this would cause the decision of not to do anything. This is what's happening today, basically. After a period in which we built everything, dams and reservoirs, and we tried to really force a massive exploitment of natural resources, then we got concerned, of course. We got concerned because we noticed that the environment was being affected, impacted. And therefore, after the concern, the current reaction is not to do anything anymore. Like now it's almost impossible to build a new dam, which, you know, I think it's a good thing. But in any case, sometimes it's not, because sometimes you need it. And the correct approach should be that if the dam is needed, we should build it. If we don't really need it, we should forget it. But if you just take the decision not to do anything anymore, then it's a problem. And therefore, this is the current behavior with respect to environment. We are so concerned that very often we don't do anything because we don't want to take the risk. And here there is a nice example, which is the gambler's paradox, and I think it's a nice example. So I wanted to skip it, but it's nice. So let me just spend a couple of minutes. Let's suppose that you participate to a gamble, to a game, which is gambling game. Gambling is gioco d'azzardo in Italian, and let's assume that you want to maximize the expected value of the money that you can win. So you have, in a gambling game, you have to take a decision. Like, of course, in this case, the experiment is tossing a coin. And no, let's say that the experiment is generally a game where the probability to win is 60%. It can be like you have to guess the next value of a variable, and you have a probability of 60% to be right. So it's a favorable situation, because you know, if you have a probability of more than 50%, it means that it's likely that you win, likely more than average. So it's a favorable situation. And let's suppose that when you decide, you say, okay, I want to maximize the expected value of the money that I win. And so if you compute your expectation, and let's suppose that you have an amount B, which is bet, your decision is, how much should I bet? So, of course, in a gambling game, you have to guess the outcome, and then you bet some money. And let's suppose that your decision is, how much money? What is the value of B that I should bet? And let's suppose that you have, of course, an amount of available money, which can increase if you win, and can decrease if you lose. So, of course, what would be your perception? Okay, your perception could be, I don't play the game because I don't want to gamble. Okay, let's exclude this situation. Given that you have a 60% probability to win, it's wise for you to bet. And then you have to take this decision. So, of course, a decision could be, let me maximize the expected value of the money that I win. So what is the expected value is 0.4 times 0, because if I lose, the probability is 0.4, and if I lose, I win 0, plus 0.6, the probability to win, times 2b. Why 2? Because the game is such that if you win, you get 2b as a winning sum. Okay, so you see that the expected value is clearly increasing with increasing b. So this means that accordingly to this criteria, if you want to maximize the expected value, you should anytime bet all the money that you have, which is clearly nonsense. Because, of course, your guess would be, I should bet, but not all the money, because if I lose, and I can lose with probability of 40%, then I lose everything. So, this wouldn't be a good solution. So to take the expected value approach wouldn't be a good solution in this case. On the other hand, if you want to minimize the risk, you wouldn't bet, which is not reasonable as well. So if you take the precautionary approach, you wouldn't bet, which is not reasonable as well. Because given that you have a probability of 60% to win, of course, you should bet. So what is the right solution? The right solution is, it depends on you. Are you willing to risk or not? If you are willing to risk, you should bet a lot of money, but not all the money. If you are not willing to risk, then you should bet with a reduced amount of money. It's your personal decision. So we need an approach to take this decision, depending also on our willingness to risk. So this is the subject of our next lectures, and it will be, you see the conclusion. Maximization of the expected value would be unreasonable, but also not to bet would be unreasonable. So tomorrow for 1 hour we will deal with, and then Monday for 1 hour, for a couple of hours, we will deal with this problem, taking decisions in the presence of uncertainty. Okay, I think we can stop here.